Hello class, today we begin chapter 8. We're on lesson number 1. Chapter 8 deals with exponents, and exponents are critical in all of your math going forward. You're going to have to really understand how to use exponents, and it's very important because if you understand how they work, it'd be a lot easier than actually doing the multiplication. We know that exponents are expressions of multiplication. So when we have, for instance, x squared, or let's take a number, a simple number, and let's put it on the board. And we know that when you square 5, right, that would be equal to 5 times 5, right? And we know that 5 times 5 is equal to 25. So, but what happens when you have x squared? Well, that would be x times x. But again, we don't know what x is yet. And when we have x squared built into an expression or an equation, there may be opportunities to further simplify. For instance, we have over here 5 squared divided by 5, right? Which is really 5 to the first power. Well, we're going to learn a simple way to multiply. Well, 5 times 5 in this case divided by 5, and we know that you can cancel out these two 5's and the answer would be 5. Well, similarly, if we had, let's say, x squared divided by x, well, how do we handle that? Well, we would have x times x, and that's divided by x. Cancel out the x's and you'd end up with x. Well, we're going to learn, for instance, this would be x to the first power. We're going to learn things such as math, where we could just simply take the base and do some simple math rather than sit here, because when it's only to the second power, that's easy. Imagine if this was to the 23rd power. How many x's are you going to put across here? So we're going to learn a lot of things on exponents. But we're going to start reading here. Let me just clear up my board. And I do encourage you to pay a lot of attention, close attention to this chapter, because again, it is one that's going to be critical for the rest of your math lives. So let's, now that I've cleared the board, let's begin reading. We have these chickens here, and it says, did it ever occur to you that with all the eggs we've laid, there should be more of us? Well, we know where those eggs are going, right? Right into the frying pan. Now, if every chicken egg produced a chicken, there would very quickly be many more chickens in the world than human beings. The number of chicken eggs produced annually throughout the world is about 390 billion. This number is so large that even though it is easy to name, its size is very difficult to comprehend. So if we took these 390 billion eggs, and if they were packed into cartons, and the cartons were stacked in a pile 100 feet long by 100 feet wide, okay, so think of 100 feet. 100 feet would be about 30 yards, 33 yards, right? Think of a football field, okay? And I believe like from sideline to sideline, you're probably going to get somewhere close to 100 feet. So imagine just like that whole side of a football field just being laid out with eggs. Now you stack them, and they would be 38 miles high. So that's quite a bit. Now we start understanding the power of this number. So the size of a number such as 390 billion depends on the number of zeros needed to write it. Adding a zero at the end gives a number that is 10 times larger. The removal of a zero results in a number that is 1/10. Well, let's take a look. Take a number. Let's take the number 1. We add a 0, which is basically 10 times, right? If we remove a 0, it's 1/10 of the original number. Okay, so we had 10, 1 is 1/10. So understanding that you can play around with the 0, handling the 0 is really our goal here. The number is going to be what it is, whether it's 390 billion. You'll see there will be other numbers that we deal with in the subsequent lessons. But you can take very large numbers, even very small numbers, and if you know how to handle the zeros, you'll be able to express it in a much more simpler fashion. Okay, and it will also help you with the math going forward. So the removal of 0 results in a number that is, excuse me, 1/10 as large. To prevent mistakes that might result from handling so many zeros, Large numbers are often written in a form called scientific notation. Now let's take a look over here at the top of 341, and we can see scientific notation is based on powers of 10. Now, from the table of sum of the powers of 10 below, it's easy to see that in each case the exponent is, and we can see the 10 to the, or 10 squared, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, going down, right? Now notice we have tens, 2 tens, 3 tens, 4 tens, all the way down. But also notice that the number of zeros in the number is in there. So it's easy to see that, for instance, 10 squared, we have 100, which is 2 zeros. 10 to the third has 3 zeros, which is 1,000. All the way down to the bottom, 10 to the 6 has 6 zeros. That's 1,000,000. Okay? So we can see, rereading this sentence, from the table of sum of the powers of 10 below, it's easy to see that in each case the exponent is the number of zeros in the number when it is written in decimal form. So the number, and we have this number, I'd have to go back and start with the first zeros and say thousands, millions, billions, trillions. What's after a trillion? That would be a quadrillion. So 1 quadrillion, for example, could be written as 10 to the 15th power. You have 1, 2, 3, 4, 5 groups of zeros here. 5 times 3, there's 3 zeros in each. It's 15 zeros. So because it contains 15 zeros, we write it as 10 to the 15th power. It also follows that the number 10 can be written as 10 to the first power. Now, if we take the annual production of chicken eggs, which is 390 billion, we can write that, and now here's where exponents kick in, and let's go to our board and let's see what they're doing here. I get the wonderful task of writing all of these zeros. Okay, so there's one group. I believe there are 3 groups of zeros here. Okay, so again, when I look at these big numbers, I have to start, well, these are thousands over here, right? And then these are millions, and so this must be billions. So I have 390 billion. All right, so let's remove our check marks. Now let's see what they're doing. We could say that 390 billion is 390 times 1 billion, right? That's simple math. So let's go ahead and express that. So we have 390 times 1 billion. Now, we can write this in exponential form, and we would have 390 times 10 to the, how many zeros are there? 9, 10 to the 9th power. Okay, so now we're well on our way to expressing this in scientific notation. It's there, but it's not quite there yet. Now, we also know, if we were to do it over here, let's see, I could express it, I'll go right underneath. We could have written this as 3.9 times 100 billion. Now, why would we do that? Well, let's just take a look. This is going to help you to see how scientific notation works. Okay, I believe I need one more zero. Yeah. So, if we had 390 billion, we know that we had 390 times 1 billion. We could also say that 3.9 times 100 billion, because we have 3 100 billion and another 0.9 100 billion, which 300 billion, are you seeing it? 300 billion, and there's one that's it's almost 400 billion, right? So we can see that 3.9 times 100 billion again is an equivalent expression of this number over here. We're just simply producing factors here, and really our goal is to get to a number like 3.9. You're going to see in scientific notation. So, and we can express this as how? Well, we can go 3.9 times, how many zeros do we have now? Well, we have 3, 6, 9, 10, 11. So we have 10 to the 11th power. Okay? So now we have removed all the zeros. In fact, we've gotten this down to a simple number as 3.9 times 10 to the 11th power. And this is scientific notation. Now, a number in scientific notation is in scientific notation if it's written in this form, a times 10 to the b power. But there's also something you need in which a is a number that is at least as large as 1 but less than 10. So we could say, we can have a is greater than or equal to 1. Okay, it can be 1, but it has to be at least 1. It can't be a decimal, it can't be 0.9. So it's 1. All right, it's greater than or equal to 1, but it also has to be less than 10. It cannot be 10. It could be 9.999999 and spend the rest of your life putting nines there, and that's okay. But it cannot be 10 in itself because now we have 2 digits to the left of the decimal point. Our goal basically is to have 1 digit to the left of the decimal point that is not 0. Okay, so as I said, 0.9 would not qualify. Okay, that would not qualify. 1.0 would qualify. 2.3 would qualify. 5.5673 would qualify. Going all around the board, 9.999, and we can write nines forever. As long as we have 1 digit that's not 0 to the left of the decimal, then we're in good shape. Okay, so that's really the simple explanation of scientific notation. Now let's turn over. Actually, let's get rid of all these wonderful nines. I'm going to need a little space here maybe. If we compare, let's take a look. If we compare top of page 342, if we compare 390 billion with its form in scientific notation, 3.9 times 10 to the 11th power, we can see that the decimal point has been moved from the end, okay, 11 spaces. Look at the number of spaces. We can go back to the board here, and we can see we moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I ran out of computer ink. That would be the 11th. That put us at 3.9, okay, which is down here. So we're at 3.9 and we moved over 11 decimal places, okay? So in doing that, we can easily see that 3.9 times 10 to the 11th power is the number we had, okay? We see that the decimal point has been moved from the end of the number to just after its first digit. So it's the first digit, and again, you wouldn't have 0, like you wouldn't have a 0 over here, would you? You wouldn't. You could express this with a 0 here, but it wouldn't make any sense. We started with 3. So that's why we're not allowed to go all the way here. Now we could certainly express that as a value. Okay, I could have said 0.39. All right, 0.39, that means I would have gone over 12. But though this is a true expression, it's not in scientific notation. Scientific notation requires that this number be, well, let's just say anything from 1 to 9, and that's it, 1 digit. Okay? Now, the point has been moved 11 decimal places to the left, and the 11 has become the exponent of 10, or the exponent of 10. The decimal point is placed just after the first digit, so that when the number is written in the form of a times 10 to the b power, a will be at least 1, but less than 10. The number of places that the point has been moved to the left becomes the exponent b. So we have some examples here. We see 5,000 is equal to 5 times 10 to the 3rd power. That's why I need a little space here. And let's just go ahead and just see how they did that. Well, we had 5,000, right? And they have a little comma. That's a comma, not a point. And so if we were writing this in exponential, or excuse me, scientific notation, we want to get to the 5, and we would move 1, 2, 3. So we would express that as 5. You can say 5.0 if you wanted to as well, times 10 to the 3rd power, because we moved 1, 2, 3 decimal places. Okay, let's take a look at the next one. We have 450. Okay, now here we're going to move over 1, 2 decimal places. We're going to end up with a 4.5. Don't lose that 5 over there. And since we're going to multiply, that looks more like an x and not a times. So let's put the big times. 10 to the second power, because we moved over 2 places. Now we have 12,005. Okay, now this 5 is hanging all the way out here. Well, if we were to express this in scientific notation, we'd have to move over 1, 2, 3, 4 places, so we know the place is 4. That's going to be our exponent, our b value, but we would have to express the decimal depending upon the accuracy and what you're being asked. But being it's written as it is and we weren't told, we should express this as the decimal, including that 5 all the way at the end. Okay, so it's 1.2005 times 10 to the 1, 2, 3, 4 decimal places. Okay, so it would be 1.2005 times 10 to the 4th power. Okay, so we see decimal form being turned or converted into scientific notation. So that's the end of this lesson.